It's a pleasure to be here. So yes, I'm Nigel Brandon. I'm head of the Hydrogen and Fuel Cell Supergen Hub, which is funded by the Research Councils. It's an academic led hub, but has a whole body of industrial partners and advisors, including folk like Sam and Ralph. So it's a pleasure to be here. We also have our Sustainable Gas Institute at Imperial College, which is looking at all issues around gas and its sustainability. That includes natural gas and hydrogen and biogas. And I'll give some web links at the end if people want to go and look at a bit more detail. Just a couple of opening comments, and this is reflective of some of the numbers you've already seen, but I think it's a very helpful way of looking at the energy flows that we have in the UK. It comes from my colleague Grant Wilson at the University of Birmingham, and I'm grateful for Grant for providing it. And it reminds us that we have the red squiggly line at the bottom there is the flow of energy as electricity. The horizontal line is the flow of energy as liquid fossil fuels, that's gasoline and diesel primarily for the transport sector. And the blue line with this big seasonal variation is the flow as natural gas. And it's transitioning across all of this that, of course, is the challenge for us for net zero. And it picks up on the points that Sam and others have made, right? Which is how do you decarbonize? It really gets extremely difficult and expensive to decarbonize all of that energy flow with electricity alone. And that having some energy flowing as low carbon molecules like hydrogen, or indeed other low carbon carriers like green ammonia, may give us the lowest overall cost to energy decarbonization, and that's what really matters. So this kind of purist debate about whether it should all be electrons or molecules is not terribly helpful. It actually will need both. And whilst we're focusing on carbon, particularly in terms of the air quality issues in cities and the transport implications of that, this is a little bit old now, but it shows you a NOx map of London with high NOx levels breaching EU regulations around the main arterial roads through London. So it's clearly a fact that we need to think not only about carbon, but air quality, and hydrogen has a role to play with that, particularly if it's used as a transport fuel and converted through a fuel cell. There was a question, I think, in the chat about, which kind of implied we might burn hydrogen, and I don't think we will. Form of combustion engine, not on a road vehicle anyway. And that's not to say we might not consider it in gas turbines for power generation, or possibly even for ships. But I don't see it for road transport. I think it's a fuel cell conversion. And this is my picture of a similar picture you've seen before, showing that hydrogen is really an enabler for an energy system, so we don't need to look at that anymore. In terms of the costs of hydrogen, and I can understand why, it can be a difficult conversation about green hydrogen and blue hydrogen. I'm an electrochemical engineer. I mainly work on the electrochemical technologies. I just want to reinforce Sam's view that we need both blue hydrogen and green hydrogen. We need all the low carbon hydrogen we can get. And today, the most expensive form of hydrogen is green. Green hydrogen is a lot more expensive than blue, and blue is more expensive than unabated hydrogen, which of course you would expect, because unabated hydrogen, we haven't got to go through the carbon capture step. But if we start to look at the prospects for cost down on green hydrogen, this comes from a report from IRENA. It's quite a useful report if you want to go, and it's publicly available. I had nothing to do with the report, but it takes a fairly rosy-eyed view of where costs may come down. But I guess the key point to take from it is that somewhere between 60 and 80% of the cost of green hydrogen, so hydrogen from electrolysis powered by renewables, is the cost of the renewable electricity. So the biggest driver here, in terms of the question that was asked about the tipping point of green versus blue, is the cost of the renewable electricity. And all of the price assumptions or future cost assumptions around green hydrogen are really very sensitive to that. And therefore it will vary depending where you are in the world and the price of renewable electricity. There are certainly some commentators who would say that once you get down to around $30 a megawatt hour, then your green hydrogen should be cheaper than blue. But as Sam has pointed out, actually it's quite a bit more complicated than that, and depends on many other factors as well. But suffice it to say, as we continue to see the falling price of renewable electricity and we continue to see innovations in the electrolyzers themselves, that should help drive down costs. but green has a journey to go on before it's cost competitive with blue hydrogen. So I just wanted to kind of spend the rest of my talk talking about where things are today in terms of the transport piece. And we're followed by Ralph, who I'm sure will give us a much more detailed view of the work he's and his colleagues are involved in at Jaguar Land Rover on this, but to kind of a broader perspective of where hydrogen fuel cell technologies are for transport applications. And it's really that integration of hydrogen as the energy carrier on the vehicle and the fuel cell as the highly efficient energy conversion device that takes that fuel and turns it into electricity to then produce an electric vehicle that we're talking about. And of course, Toyota have been leading in this space for a long time. This is the Toyota Mirai that we have at Imperial College London. And they are available in small numbers in the UK. Toyota have brought out a more recent version of this. And of course, Hyundai have their Nexo as well. These remain relatively expensive vehicles to buy, but in terms of an electric vehicle that can drive a good range of 300 to 400 miles, and you can refuel in a few minutes, using, by the way, at a Shell forecourt, an ITM electrolyzer, which is the same type of electrolyzer that Sam referenced in that very large-scale project that's happening in the UK. So that's really where I'm sure cars are, and we'll hear more from Ralph, I'm sure. As previous speakers have alluded, both Sam and Claire, I think the big opportunity in transport is also in heavier duty vehicles where the energy requirements are higher and there's a less obvious, you're competing less obviously head to head with battery electric vehicles. The Optare bus at the top there is a collaboration between Arcola Energy, or a UK-based fuel cell integrator, and Optare, which is this hydrogen fuel cell double-decker bus manufacturer in the UK. You've got Wrightbus as well, very active in this space in Ireland. And of course, we've had those RV1 fuel cell buses as part of an EU program running in London for a long time. But there are big programs globally around hydrogen fuel cell electric buses. I think a rapidly emerging area is around hydrogen fuel cell electric trains. And that bottom picture there shows the Breeze, which is been developed for the UK market by Alstom, which is a hydrogen fuel cell electric train designed to replace diesel units on sort of more urban train lines. Sorry, the photograph at the top is the Breeze. The photograph at the bottom is the Hydroflex, which is on trial in the UK. Heavy duty and off-road, so trucks and off-road vehicles are a really interesting application area for hydrogen fuel cell electric powertrains, again, because their energy requirements are such that it's quite hard to envisage technical solutions which will deliver that using batteries alone. That's the picture there of JCB, who are very active in this space. It's interesting to see Bosch's announcements around hydrogen fuel cell powertrains, again, focusing initially on trucks. And certainly in all of the conversations I'm having with folk, these kind of heavy duty vehicles are where a lot of the interest sits at the moment. And then I should say that all of those fuel cells use a polymer fuel cell, which is a lowish temperature fuel cell, runs about 100 degrees centigrade, uses platinum group metal catalysts. Johnson Matthey are very active in that space as well. But just to say, we do have a UK company called Ceres Power, which I'm declare an interest as one of the founders, producing a higher temperature fuel cell. It's a metal supported a solid oxide fuel cell, as it would be known, and that's being put into buses in China. These are not hydrogen buses. These are actually buses running on fossil fuels, but this type of fuel cell will run very well on those, but they also run very well on hydrogen. So this is another type of technology that is useful for some types of transport applications, including ships and trains and so on as well. So I'll park it there. That's my quick whiz through my opening comments, and we have some website links there, or you can email me if you want links to any of the information I've provided. So thank you very much.